So we were giving example of the quotient ring construction. So far we have two, z mod n z, which is just integer modulo n. And then we saw that if you take the one variable polynomial ring with real coefficients down here and quotient out by the ideal generated by x square, then that quotient is isomorphic to this ring S that we had seen before. S is isomorphic to R2 with the usual addition and this funny multiplication. Okay. And the way this went was you defined a map from one variable polynomial ring to S, taking a polynomial to its value at 0 and its derivative at 0, those two numbers. You verify that this is on to ring homomorphism and the kernel is exactly all multiples of x squared. So if you have a on-to ring homomorphism from one ring to another ring, on-to ring homomorphism from one ring to another ring, then the domain ring modulo the kernel of the homomorphism is isomorphic to the image. That's what the first isomorphism theorem says. So here I have a on-to ring homomorphism from this ring to that ring. The kernel is all multiples of x squared. So by first isomorphism theorem, we get that the quotient Rx mod ideal generated by x squared is isomorphic to S. And this is typically how identification of quotient rings go. This format is fairly typical. You don't want to define a homomorphism directly from the quotient. What you want to do is you want to define a homomorphism rather from this mother ring, so to say, and show that the kernel is what you want it to be, and then apply the first isomorphism theorem. And that's often how first isomorphism theorem gets applied. Okay. So the third example that I want to do is the more general, you can think of it as a more generalization of this. I want to describe more generally what does Rx mod an arbitrary ideal look like. Okay, we won't get such a concrete description because I don't know what f exactly is, but we'll want some kind of a description. Let me try get some space here. I still want to keep the right hand side. So let's go for example 3. I'll again start with one variable polynomial ring. I'm just taking real number coefficients, but if you wish, you could change it to rationals. You can change it to whatever field you want. We'll just keep it real number just to be concrete for now. And let's fix a polynomial of degree n. So it looks like a0 plus a1x plus etc. a(x) to the n. This last coefficient is non-zero. So that's a degree n polynomial with real coefficients, let's say. And the question I want to address is that question, describe R mod f. Or if you will, sometimes we write f, sometimes we write fx, means the same thing. Okay, it's not pretty clear what it means, this question even means, but here is what I want to actually prove. And this claim actually gives a description. So what I want to say is that the elements of this ring, let's call this quotient S, as we did in the previous example, are in bijection with polynomials in R of degree at most n minus 1. N, remember, is the degree of the f you fixed. Then the elements of the quotient ring are in one-to-one correspondence with the polynomials of strictly lower degree. And how does this grow? Let's give a sketch. I'll at least give you the map. More precisely, actually I can make this claim more precise, I suppose. More precisely, given any coset element, call it, I don't know, A in S, this quotient ring, there exists a unique polynomial R of degree strictly less than n, at most n minus 1, such that this element A is the coset of R. Let's be consistent. Let's just write R. So every coset can be uniquely represented by a polynomial of degree strictly less than n. And let's try to sketch a proof of this. So let phi from R to S be the quotient map. Now S is R mod F. So when you quotient out by an ideal, you have this quotient homomorphism. Look on the right hand side, right here. It takes an element to its coset. So it takes a G to G plus all multiples of F, that coset. I want to know that everything on the right hand side looks like R plus F, where R actually has degree less than or equal to n minus 1, and that this representation is unique. Okay. So a typical element of S looks like this. So a typical element of S has the form G plus F, where G is some polynomial. Where do I get this R? I need a polynomial of degree at most n minus 1. What you do is you divide G by F. So using division with remainders, this is the crux of the argument. Remainders we can write, so I'm going to divide G by F. I get a quotient and a remainder for some Q R in the polynomial ring, and degree of R strictly less than n, or less than or equal to n minus 1, right? Because the degree of R has to be strictly less than the degree of F, which is n. claim. So notice that G minus R is a multiple of F. So this lives in the ideal generated by F. So G is congruent to R mod F. So the coset of G is the same as the coset of F. So every element of S has the form R plus F for some R of degree less than or equal to n minus 1. That's half of the argument, that there exists an R of degree at most n minus 1 such that any element can be represented by that. And now for the uniqueness part. So this is the existence part, if you will. And now for the uniqueness part. So suppose A in S again, and you wrote it as represented by two polynomials, R and R1. Where both have degree strictly less than or equal to n minus 1, strictly less than n. So an element of S has been represented by R, also has been represented by R1. I want to show that R is actually R1. So R and R1 live in Rx, right? And this is fairly straightforward. R plus F equals R1 plus F implies note that this implies R minus R1 is in F. Two things have the same coset if and only if they are congruent mod the ideal, which means that the difference is in the ideal, i.e. F divides R minus R1. But now you look at degrees. R and R1 both have degree less than n, so this difference also has degree at most n minus 1, whereas this guy has degree n. So a degree n guy is dividing a degree, something of degree less than or equal to n minus 1, which means this thing has to be 0. You cannot divide the thing of lower degree, because dividing means that R minus R1 is F times another polynomial. And when you multiply polynomials, the degree adds up. It cannot go down for some G. So the only conclusion is that R minus R1 has to be 0. So R has to be R1. So every element of S can be represented like this by a degree n minus 1 or a lower degree polynomial, and that polynomial is uniquely determined. Okay. And when you add these, you just add them normally, and when you multiply them, when you multiply one of these guys with another such guy, you get this. And this might happen, it might happen that this now has degree more than n, but then you divide by f and take the remainder again. So let's say remainder when R times S is divided by F. That's a temporary notation. Yeah, so that's how the multiplication works if you want to represent everything in terms of polynomials of degree at most n minus 1. And we'll talk more about this description.